Hello everyone, welcome to lecture number 42 in this NPTEL course on Riemannian geometry. So in the previous lecture I stated this very fundamental theorem called the Hopf-Rinow Theorem, and we proved parts of it, but we left one key step which is what I will prove today and hence complete the proof of Hopf-Rinow. So let me remind you of what the statement was. The statement is that the following conditions 1 to 4 are equivalent. The first condition is that M comma D is a complete metric space. So remember we defined using the Riemannian metric, we defined a distance function on M. So the first condition says that M comma D is complete. The second condition says that M comma G is complete as a Riemannian manifold, geodesically complete, which just means that for all P in M, the domain of the exponential map at that point is the entire tangent space. Then the third point was that this condition holds at some P. So there exists a P where whose domain of the exponential map is equal to the whole tangent space. So in other words, to check geodesic completeness, the Hopf-Rinow theorem is claiming that it is actually enough to check at each point, right, check at some point rather. So if at some point EP is equal to TPM, then it is geodesically complete. The fourth point is that the Bolzano-Weierstrass property is satisfied, namely all closed and bounded sets are compact. And moreover, all of these imply the following basic fact, that for all points P and Q in M there exists at least one minimal geodesic connecting these 2 points. So remember, minimal geodesic was a geodesic which minimizes which actually attains the distance between P and Q. So it minimizes the length of among all possible admissible curves connecting P and Q. Okay. So the proof of this went via the following sort of flow chart. We first proved that 1 implies 2 and then 2 implies 3 is a triviality, and then I claimed that 3 implies this key property which I labeled by hashtag. I will remind you what this key property is in the next slide, and then the point was that 3 plus this hashtag property implies the Bolzano-Weierstrass property, and then the Bolzano-Weierstrass property implies completeness of the metric space. This is a purely metric space argument, right. And then of course if one takes 2 and applies this hashtag property for all P, then that implies 5. So that completes the proof of Hopf-Rinow. Okay, so let me now remind you of what this property hashtag was. Okay, so let P be a point in M such that the domain of the exponential map is the entire tangent space. Then for all other points Q in M, there exists a minimal geodesic from P to Q. Okay. So hashtag is basically property 5, but where you are fixing a point P where whose domain of the exponential map is the entire tangent space. Okay. Right. So the point of this lecture is to actually give a proof of this hashtag property, thereby completing the proof of Hopf-Rinow. Okay. Right. So what is the difficulty? So let us say you have a point P here. So you should imagine that you have a sort of cannonball machine at P, and Q is a target that you want to shoot a cannonball at. So the key thing really to understand is what direction you shoot in, right. So if we know what direction we want to shoot in, then just by applying the exponential map of that vector would take you from P to Q, and we know that the exponential map is defined everywhere by the hypothesis, and hence we would be done. So the key point is to know which direction to shoot in. Okay. So for that let us set down some notation. So let Q let the distance between P and Q be L, and we fix and epsilon smaller than L, okay, such that if you look at such that there exists some epsilon naught bigger than epsilon with the property that that the exponential map from the ball of radius epsilon naught in the tangent space this is a diffeomorphism. Or in other words, you look at this is a geodesic ball of radius epsilon naught. Okay. And now we consider the boundary of the geodesic ball of radius epsilon, okay. So so in other words, I want this is a geodesic ball of radius epsilon for all epsilon less than epsilon. Okay, so now I basically fix one such epsilon and consider the boundary of that geodesic ball. So let me draw it here. Okay, so this is the boundary. Now because this is the diffeomorphic image of a boundary of a ball in the tangent space, this is going to be compact. So note that this is going to be compact. So then there exists a P naught which is closest to Q, right, such that the distance of P naught to Q is equal to the infimum of the distance of x to Q over all x in this boundary of the geodesic ball, right. So by compactness, in fact, the infimum will be a minimum, and so let us say the minimum is attained at this point P naught, okay. So let me draw this point P naught here. So this really tells us what direction to shoot in. So the point is that P naught, because it belongs to this geodesic ball or at least the closure of the geodesic ball, it is basically the exponential of some vector v, it is the image under the exponential map of some vector v, right. So that vector v tells us where to shoot. So I just take the geodesic in that direction. So in other words, let okay, so let P naught be given by the exponential of V naught, where V naught is some tangent vector at P of unit norm, okay, of unit length, and let gamma of T be the corresponding geodesic, okay. So my claim is that gamma at L, so remember L is the distance between P and Q, is actually Q, okay. So then I would be done, because I have found a curve of length exactly L which connects P to Q, and L was the distance between P and Q, so gamma will have to be a minimal geodesic, okay. So if I prove this, I am done. the key point why the key sort of observation why this is likely to work is the following. So let me make a remark. So note that if gamma were a minimal geodesic, let us say unit speed geodesic, from P to Q, right. So then if you look at gamma of epsilon, so that is the place where this hits your minimal geodesic hits the boundary of the geodesic ball, then the distance to Q would be L minus epsilon, and this would in fact be the infimum over all the distance of over all points in the geodesic sphere, right. So this tells you that your intuition that this you look at this point P naught which is closest to Q and then shoot in that direction, your intuition is correct, because eventually if gamma would be a minimal geodesic, then this property would be satisfied, okay. Alright, so so to prove the claim, it suffices to prove the following. So let me write down another claim, okay. It suffices to prove that if you look at the distance from, let us say gamma of t to q, so if you look at the distance from gamma of t to q, then that is L minus t. So I am going to call this equation star t, okay. So clearly if you put t equals L in star t, that would imply that the distance of gamma of L and q is 0, which implies that gamma of L will be equal to q, right. So that would complete the proof, okay. So now how do you prove this this modified claim? So proof of the second claim or the modified claim, right. Okay, so so I am going to do the following. So let I be the set of all times in this interval such that star t holds, okay, and let capital T be the supremum of I, right. So of course even to take the supremum we first have to show that I is actually non-empty, right. But in any case, what is the goal? The goal is that L belongs to I, right. So then we will be then basically we will be done, okay. Alright, so right, so sorry, the goal will be to show that okay. Alright, so here is the first subclaim. So as I said, one has to first show that this interval I is non-empty, right. So the first subclaim is that epsilon belongs to this interval. That means that the distance of P naught to Q is actually equal to L minus epsilon. So note that this actually will imply that that T belongs to I for all T between 0 and epsilon, okay. Alright, so so how do you prove this? Okay, so first note, by the triangle inequality, so if you take the distance from P to Q, which by hypothesis, by our notation is just L, this is less than equal to the distance from P to P naught plus the distance from P naught to Q. Okay. Okay, but what is the distance from P to P naught? Because we are working with a geodesic ball, we know that in a geodesic ball the radial lines are all geodesics, are minimal geodesics. So this distance is going to be epsilon, right. So this is going to be epsilon plus this, and because I am assuming that epsilon is less than L, I can take this to the other side. This implies that the distance from P naught to Q, the distance from P naught to Q is at least L minus epsilon. If it were equal to L minus epsilon, then I am done. So suppose we have strict inequality, then I want to get a contradiction, so we are arguing by contradiction. So if there is a strict inequality, you can actually make sure that it is actually bigger than L minus epsilon for plus delta for some delta positive. Okay. All right. So then there exists an admissible path from P to Q. Just by the definition of the distance function, there exists an admissible path which has unit speed such that the length of the admissible path is strictly less than L plus delta. Why? Because L was the distance from P to Q. Remember the definition of distance, that is taken over the infimum of the lengths of all curves connecting P to Q. So if the infimum is L, if you take something slightly bigger than L, there must be a path whose length is between L and L plus delta, otherwise the infimum would have been L plus delta instead of L, right. So this is just from the definition of the distance function. Okay. So now you take the distance from P to Q. Okay. Sorry, let us do the following. So let P1 be the first point be the first time right, the first point where sigma, where this curve sigma hits the boundary of this geodesic ball, right. So then let V1 be the derivative of sigma at 0, and then note that that the distance from P to P1 will actually be again epsilon, because the points on the boundary of this geodesic sphere, they are all at a distance of epsilon from P, because radial lines are just geodesics, right. Okay. But then as a consequence of this, if you take the distance from P to Q, then that is sorry, the distance of P1 to Q. So maybe let me just draw a little picture. So let me draw a little picture on the next page. So the situation was, we have our P here, we have our Q here, right, and this was our sort of P naught. Now you have another curve connecting, this time it actually connects P to Q and it hits the geodesic sphere at this point P1. So then let us look at the distance from P1 to Q, right. clearly that is going to be the less than equal to the length of the part of sigma between P1 and Q. So that is so the distance from P to P1 is epsilon, and P1 is actually equal to the exponential at P of some epsilon 1 times V1, where now epsilon 1 will of course be strictly bigger than or equal to epsilon, right, because sigma is a curve connecting P to P1, the distance between P and P1 is epsilon. So the length of sigma, the part of sigma between 0 and epsilon 1, that should be bigger than epsilon, right. Okay. So this is the length of the distance from P1 to Q is less than equal to the length of the part of sigma from epsilon 1 all the way up to L plus, right, all the way up to L1, right, where L1 is basically just the length of sigma, which we by choice is less than L plus delta. Okay, so what is this length? Because sigma is unit speed, this is precisely L1 minus epsilon 1, but epsilon 1 is bigger than epsilon, so this is less than, and L1 is bigger than is smaller than L plus delta, so this is bigger, this is less than equal to L plus delta minus epsilon. Okay. But by our hypothesis this is strictly smaller than the length than the distance from P0 to Q, right, that is what we were assuming, that this distance is bigger than L minus epsilon plus delta. So we have found another point P1 on the boundary of the geodesic ball such that the distance of P1 to Q is strictly less than the distance of P0 to Q. But remember what was the definition of P0? It basically attained the infimum of the distance to Q over all points on the boundary, right. So that is a contradiction. That contradicts the choice of P0. So our assumption that the distance from P0 to Q was strictly bigger than L minus epsilon is incorrect. So that means that epsilon belongs to the interval. So one has to have equality, that the distance from P0 to Q has to be L minus epsilon. Okay, so that proves the first subclaim. The second subclaim is rather simple, is that the supremum actually belongs to the interval I. Okay. So why is that? That is because capital T is the supremum, so there exists a sequence of times Tk. So in particular supremum is a limit point, so there exists a sequence of Tks such that Tks converge to T, but then the distance from gamma capital T to Q by continuity of the distance function and of the curve gamma, this is simply the limit as k goes to infinity, the distance of gamma Tk to Q, but because each Tk belongs to this interval I, the equation star Tk holds. So this is simply L minus Tk, but then that is just L minus T. So that shows that star capital T also holds, or in other words capital T belongs to this interval I. Okay. Alright, so finally I need to prove the following subclaim, is that capital T is equal to L. So then this in particular will imply that that this interval I is the entire interval 0 to L. Okay. So what is the proof of this? So suppose for sake of contradiction capital T is strictly less than L. Okay. So let P prime be gamma of t. So again let me draw a picture. So we have our P here, we have our Q here, we shoot in a certain direction, but instead of reaching Q it sort of terminates somewhere, which I am calling gamma capital T. Okay, and then it just goes somewhere else, it does not go back to Q, right. So this means that what we are claiming originally is not true, our gamma does not reach all the way up to Q. Okay, so then the idea is that what you did at P, you do the same construction at this P1. So as before, let U P1 this is P prime, let me fix the notation. So this is P prime. So let P prime epsilon prime be a geodesic ball, and let P naught prime be on the boundary such that the distance from P naught prime to Q, so exactly the construction from earlier, is the infimum of all distances from x to Q, where x now varies over this new, the boundary of this new geodesic ball. Okay. Right, so that gives us a P naught prime here. Okay. So now my sub claim is that gamma of t plus epsilon prime is precisely P naught prime, and that will right, and t plus epsilon prime actually belongs to the interval. So that will contradict the fact that t capital T is the supremum, and so then I'll be done. Okay. Okay, so why is this? All right, so let so as before, so let V naught prime be a tangent vector at P prime whose norm is 1, such that P naught prime is the exponential at P prime of epsilon prime times V naught prime. Okay. And let sigma be the corresponding geodesic. Okay. So now consider the concatenation. So in this picture, this is basically this red geodesic gamma all the way up to P prime, and then you concatenate this little sigma here. Okay. So consider the following: gamma tilde of t. So let this be gamma of t from 0 to capital T, and then for a time interval epsilon prime after that you want it to be sigma, but you have to sort of linearly adjust the time. So let it be sigma of t minus capital T for t between capital T to capital T plus epsilon prime. Okay. Okay, so then one thing to note is that the distance from P to P naught prime is going to be less than the length of this gamma tilde, right, because gamma tilde is one such curve connecting P to P naught prime, and the length of gamma tilde is actually equal to t plus epsilon prime, right, because that is the length of gamma, but gamma is minimal up to right. So, sorry, this is it's basically a unit speed curve up to for time t plus epsilon prime. So, length of gamma tilde is going to be t plus epsilon prime. Okay. On the other hand, if you take so we repeat the argument of subclaim 1 at, I mean for this new geodesic ball. So, what did subclaim 1 show? That if you take the distance from this point, which was p naught, all the way up to q, then that distance is L minus epsilon, right. So, similarly if you take the distance from this p naught prime to q, that is going to be the distance from p prime to q minus epsilon prime, okay. So, so the distance from p prime to q, sorry, p naught prime to q is actually going to be the distance from p prime to q minus epsilon prime. But what is the distance from p prime to q? Well, p prime is just gamma of capital T. So, this distance is precisely L minus capital T, okay. So, we get this important relation that the distance from p naught prime to q is L minus T minus epsilon prime, okay. But now we apply the triangle inequality again. So, by the triangle inequality, if you take the distance from, let us say p to q, then that is by our nomenclature, that is L, but then by the triangle inequality, that is less than equal to the distance from p to p naught prime plus the distance from p naught prime to q. But the distance from p naught prime to q is L minus capital T minus epsilon prime. So, we get this. So, now if you cancel out the t from both sides, this implies that the distance from p to p naught prime is bigger than or equal to t plus epsilon prime. But on the other hand, here we see that the distance from p to p naught prime is less than equal to t plus epsilon prime. That means that we have to have equality, okay, which means that this gamma tilde was actually a length minimizing curve connecting p to p naught prime, okay. So, this implies that gamma tilde is length minimizing from p to p naught prime and hence a geodesic by our consequence of the first variation formula, and hence in particular it has to be a smooth curve, okay. So, that basically means that the derivatives of so in particular that means that the derivatives of these two curves have to match up at t equals capital T. So, in particular this implies that the derivative of gamma prime at capital T has to match up with this V naught prime, which if you remember was the derivative of sigma at 0, right. So, in particular by this the uniqueness of geodesics, this implies that gamma tilde has to be identically equal to gamma on this interval t plus epsilon, okay. But then by so then this implies that if you look at the distance of gamma of t plus epsilon to q, well now because gamma is the same as gamma tilde, this is the same as the distance from p naught prime to q, which we have already proved is actually equal to L minus t plus epsilon prime. So this implies that t plus epsilon prime belongs to I, which is a contradiction, because capital T was the supremum of all such times for which supremum of all the times that belong to I. So this would be a contradiction unless capital T is actually equal to L, and we are done. Okay. So this completes the proof of this key property hashtag, and hence it completes the proof of Hopf-Rinow. Okay. All right. So in the next few lectures, I will try to analyze this question further as to if you are given a geodesic, when is it minimizing? Okay, and we will take inspiration from calculus, where if you have a critical point, to decide whether something is a minima or not, you take the second derivative, right. So taking inspiration from that, we will try to calculate the second derivative of the energy functional, because geodesics are critical points of the energy functional, right. Okay, so that is going to be the main topic of interest for the next few lectures. Alright, so that is it for this lecture. Thank you for your attention, and I will see you next time. Thank you.